So his name is Dmitry Chernukhin from Lido, and he's going to be talking about how to EIP-4788.
So, hey everyone. My name is Dmitry. So there is a meet at my last name because it's hard to pronounce, yeah, we know it. And I'm currently contributing to Lido community staking team. And let's do like a quick temperature check. Do you know what is Lido? Just raise your hands. Okay, awesome. And so quick refresher, Lido on Ethereum is a protocol which acts like a middleware between node operators and Ethereum stakers, Ethereum holders actually. And there are currently around 9 million Ether staked with the protocol. And it's always possible, I think, because of Lido principles. And I'm personally strongly for its mission. It's to make staking simple, secure, and decentralized. That's why I'm particularly interested in the community staking model, which opens a permissionless entry to the Lido node operator sets. And where is permission, then EIP-4788 comes into play. But first things first, let's take a look at the EIP. It's called beacon block root in the EVM, and like it's kind of cryptic. Someone finds it's really revolutionary and it will be very useful for Ethereum at all. But what is it all for? So even after the merge, from the smart contract perspective, there are still two separate chains, execution layer and consensus layer. And the only possible way, like form of communication between them, it is sending either. So basically you create a validator on the execution layer by sending either to the deposit contract and then a validator being created on the consensus layer with the ether you have been sent, right? And when you're going to withdraw it from the consensus layer, this ether is being like transferred back to the execution layer to the withdrawal credentials. That's it. But now with this new EIP, there is an additional way of communicate between these two layers, and it's being a block root. So basically, consensus layer now collects the block roots and push it to the execution layer as a part of the specific transaction. And to do that, there is a special smart contract which is called a block root contract. It is deployed as a pre-specified address, and it works something like this. So you select some time stamp for a slot, you send it to the smart contract, and you just receive a corresponding block root, or it reverse. It depends. And the handy thing is that the block root can be used to build an inclusion proof of a beacon block data. So who knows what is airdrop? Who just claims something for this? Okay, perfect. So you probably already know what is inclusion proof is. So imagine, so we have some airdrop, and there is a list of addresses that are eligible to claim some token, I don't know. And the usual way to do this for developers is to build a Merkle tree on top of this list. It is a special binary tree in which all of their nodes are being hashed in pairs up until the only one hash at the very top, which is called the root of this tree. And this root acts as a commitment to the whole list. It's like a checksum or something like this, and it's being stored in the contract. And then if you want to claim your tokens, you just create a proof by selecting specific nodes from the tree in such a way that a smart contract then can receive these hashes and recompute the root of the tree and compare it with the root that was stored in the smart contract. And if they match, so boom, you prove to the contract that your address is actually included in the list. So that's why it's called the inclusion proof. And the thing is that beacon structures are also trees. And on the left side, you see the definition of the beacon block as it is now. And in the process of the Merkleization, a Merkle tree is being built on top of the structure, and its root is actually beacon block root we see on the beacon chain scan, for example. And this is actual beacon block route which is being pushed by this new EIP back to the execution layer. And another thing is that you can see this structure, there is a state route which is actually is a root of another beacon structure. It is beacon state. So starting from the beacon block root, you have an access to the beacon state as well. And maybe like is proof is all we need to like bring information about consensus layer to the execution layer. And unfortunately, it's not, just because to verify proof, we also need an access to the consensus layer generalized index. Generalized index is basically like index of a node in a tree, but it is really important, and I will show you why. So in our airdrop example, there is one difference in where in the list your address is actually located. Like it may be like the second one, the third one, there is no difference at all, so it's just the like just a list, nothing else. But imagine the case. In a beacon state now, we are storing a list of good and bad anime titles for some reason, I don't know, maybe just. And you want to prove to the contract that some anime title is actually is located in the list of the good ones. So you have to show to the contract that you are pointing to the correct branch of the tree. And how to do that? And actually the answer is pretty simple. So just because the Merkle tree is a binary tree, you can just like somehow draw the path to the node. And in the binary representation, it looks like this. You just start with the one is very top in the root, and for the every left turn, you just add a 0 to the path, and otherwise you just a 1. And then you receive just a binary sequence, which is maybe it has its decimal representation, and you can enumerate just all the nodes in the tree. And actually, you can do it even easier, just because like a root has its index 1, and every left child has like index of doubled of its parent, and the right one is doubled and plus 1. That's it. So that's how you can get all the indexes of the nodes of the tree. But okay, let's take a little break from this and just think about application of this EIP. The first it is a staking pool. So with this EIP we can bring in a permissionless manner information about a validator on the consensus layer. So it is like the balance, it has its withdrawal credentials, is it slashed or not, and so on. This is also useful for staking, just because we can do like pretty much the same thing. And it is useful for like community staking module as well, just because in the permissions manner, we can now prove that the validator was slashed, for example, and we can say what withdrawal balance it had on the consensus layer as well. So basically, EIP-4788 provides a new source of truth about the consensus layer available on the execution one. And at what cost? So to prove a state for a validator state, or for the single one validator, it's cost like around 100K gas. But if you want to do it for multiple validators, like 1,000 of them, this is like enormous amount of ETH required to finish the transaction, to include it. And that's why actually trusted oracles have worked better in these cases. But still, there are like different zero-knowledge proof solutions that can be used instead, and they actually may use this EIP-4788 like as an input to verify it. So still can be useful for that. Another thing, it doesn't make sense to store all roots on chain forever, just because there is no one needed for all of them. It will be just a waste of storage. That's why actually designers of the solution proposed to store it for 27 hours. It is a window for a transaction to be included in the block, basically. So this is amount of time when like you build a proof against some root, and it is still available to be verified within this window. But the question is, what if you have to prove something really old. So what to do with that? And there is an answer to that, just because there is two historical accumulators available in the consensus layer. It is a historical roots and historical summaries. Historical summaries were deprecated, but still both of them cover the whole history of block roots and state roots of the consensus layer. And the thing is that you can access historical accumulator starting from some state root, some block root, I will say, that is available at the moment, and then you just combine this tree in the bigger tree, and you access the really old one data starting from the fresh one still available block root on the execution layer. Yeah, it is just one more thing to the whole path. And one more thing about generalized indexes. So that's the thing that they are really important to really understand that we are pointing to the correct node in a tree. But at the moment, there is no trusted way to access it on the execution layer. So we just don't have a way to ask execution layer to give me generalized indices, the index of some field of some structure. And it will depend on the application developers how to assess this problem. Just because maybe the simplest way is to just hard code it in the smart contract, and we just trust the developers, so why not to hard code it in it? But the problem is that generalized indices are subject to change. And for example, if you have a structure consisting of just 4 fields, and you are needing the second one of it, on the hard fork 1, for example, there will be this structure on the left side, and the second field generalized index is a 5. But if you have to add some fields to the structure, for example, because of hard fork requires some additional data, like it's what, for example, in Dencun upgrade, when there were additional fields related to blobs were added to the beacon state structure, this structure grows, and the tree grows as well. And it means that the generalized indices are changed. And in our example, we can see that all generalized index is not pointing to the leaf itself, but it also points to the completely wrong branch. So we should take care of this. And it's up to the smart contract developer in this case to understand how to solve this problem. Yeah, and the last problem about this EIP is that block root contract stores actually a parent block root for a slot. And the reason for this is pretty simple, just because, as I said before, there is a special system transaction to include a block root into the execution layer. So we can't include the block root in the block itself just because it will create a circle dependency. That's why the parent block root was chosen, okay, for this purpose. And the thing is that the block root contracts accept just the timestamp of a slot, and we receive previous block root, and we couldn't expect that by requesting a block root for a timestamp of a slot 12, we get a block root of a block included in the slot 11, just because on the consensus layer there is a slot when no block exists, and in this case it will point to the some slot backward in the history. And if your application is depends on the slot information, timestamp, and so on, you probably have to think about another ways to verify this data. For example, you just simply provide the whole beacon block structure and verify it on chain. It's pretty simple, and there all the information we need. So just summarize the thing. We don't know for what slot we get the block root at the given timestamp. That's the trick. So you have to figure out like somehow off-chain probably. So there is some code snippets like Solidity code if you want to look how it works from like smart contract perspective. They're trying to verify actually blocks, actually beacon state for a validator and withdrawal thing. So that's what we're really interested for a community staking module. And here is OAuth. You can grab it. It is like dedicated to this event, and actually, it's not it's not only a beautiful thing, but it's only will grant you a point in the Lido community staking space. So that's it from my side for today. Thank you. Questions? Awesome.
Could we, for example, get information that's on the consensus layer, like the withdrawal address onto a smart contract in order to, so I'm thinking about smoothing pools, for example, and on a smoothing pool, on Smooth, the smoothing pool that we have at DAppNode, we use the Oracle for, we use the trusted Oracle for a lot of the stuff, and a way of eliminating this Oracle would be if we had a way to give access to the management, give like management access to manage your subscription to the pool to a withdrawal address that you have done in your, that it's in the consensus layer when you have registered that validator. Now, is there any way that we can use this data now to give the smart contracts knowledge of who should be the manager of this validator on the execution layer?
Yeah, we can do this because in the validators in the beacon state structure, there is a list of validator structures in it, and it has withdrawal credentials field. This is just public, not public, just address to be withdrawn for. And we can bring this structure to the smart contract. It can verify it and check that, yeah, okay, these withdrawal credentials, and so this address is the manager.
Nice. It would still be extremely expensive to do that for all of the validators of a pool, for example, if this was done in Ethereum, though.
Yeah.
Can we do that on a layer 2? Can it be put in a layer 2 somehow?
Well, I didn't think about it actually, so
okay.
I have to think a little bit. So.
Maybe the previous speaker with Hyperlane or something like that.
Yeah, I don't have much experience in L2
right.
to be honest. So.
I'm just talking out of my ass. It's just
okay, awesome question, thank you.
Do we have any more questions? No? Well, thank you so much for your presentation.